who is a scientist at Los Alamos National Lab. And then my former PhD student just graduated last year, who is a postdoc at the Virginia Institute of Marine Science and Katihi. And then John King is a collaborator at the NC State who actually provide the long-term of the in situ measurement and also collaborated with me. And my former visiting student is Jie Zhu, right now a professor at the Beijing Normal University. And then some of the collaborator like Kurt Richardson is the director of Duke Wetland Center, and we have actually collaborated pretty much. And then Ji-Sun Steve McMarty is the U.S. Forest Services scientist. They also provide a lot of, the in situ measurement for this work. So it's really a teamwork instead of only I'm the person to get the work done. And before we were handling some of the technical issues, so I think like I used to work at the Georgia Tech, so our division actually belongs to School of Science. And once I got the position at Duke University, so this is the School of the Environment. And once you are in the School of the Environment, you notice people work on different aspects of the environment: climatology, hydrology, ecology, public health, law, economics. So it's kind of like one of the criteria I share with, one of when you promote it from a AP to associate professor, one of the criteria is that how you branch out your research. So that is one way I develop, some of the collaborations with my colleagues in and out of Duke to study the ecology or hydrology. And so those are the pictures. I teach a course which called the climate system, which is a required course for all the master student and PhD student. So when we talk about the climate system, we talk about there are 5 components within the climate system, like the atmosphere, hydrosphere, biosphere, land surface, cryosphere. And then we also talk about how those components interact with each other, right? So this is kind of like one of the way we talk about it. Then I thought about, I actually participated for the IPCC assessment report as well. And then when you look at those of the IPCC assessment report, a lot of times we talk about the hydrological cycle, carbon cycle. So you see a lot of papers or the chapters talking about those, right? But then when I ask you, which components in the climate system that highly links both the water cycle and the carbon cycle, but it's not similar to variable in the current state-of-art models. I would think about the wetland is definitely the answer over there. And people call the wetland ecosystem the kidney of the earth. And so this is why I was kind of talk about it. So without thinking about those of the simulate or incorporate the wetland simulations very well. So you cannot trust the IPCC models in terms of the simulation, the future projection, in terms of the carbon cycle and the water cycle, right? So that is kind of the way I kind of jump into the field, besides what really the school requires as well. And also when I was a postdoc, and I think that moment, I probably will mention, so during the period of time in 1997, 98 is a very strong El Nino years. And I happened to read a paper publishing on Science, talk about, during that very dry years over the Indonesia region, they have a spatial wetland, it's called the peatland ecosystem. So during dry years and the peat will be exposed to the air. And then the Indonesia government have this microrise project. So they tend to use fire to burn those of the peatland so that convert it into the peatland to the agricultural site for agricultural purpose, right? And then that's just the year, if I tell you the numbers, and then the global mean carbon emissions will increase by more than 10%. So it's a huge amount of the carbon release. So that is during that period of the year, I would think about it. Then the IPCC model cannot, simulate this as well, and then how we look at, the wetland. So I actually published a paper on GRL, so during my postdoc period. So I think that is pretty initial work when I think about this. So I use empirical formula to derive the hydrological cycle changes, especially the groundwater migrations or variations, so how that will influence the tropical, subtropical wetland and therefore influence the carbon cycle. So that is the initial interest of mine when I was a postdoc. So later on, once I joined the Duke as a faculty member, and then at the first couple of years, so we have 8 years of the, from AP to associate professor. So at that period of time, I didn't change. I still work on climate dynamics because the clock clicking. You don't want to ruin your stage. So I'm still working on the climate dynamics, but then once I get tenure, I think this is probably the time to work on the wetland ecosystem. So that's why, and also because at Duke, we have the Wetland Center, we also have some local collaborators, and I talked to Kyle, in the morning, and Holly. So we have Emily Bunford, and then Ryan Emanuel and others, who work on the ghost forest at Duke. So different, groups were working on this project, kind of features, or we have internal seminars. So that's actually helped me to further jump into the field. So when we define the wetland, really we're talking about, the ecosystem, their water line is about 30 centimeters above this topsoil zone, but at least 2 weeks in the growing season now. So like I mentioned, the wetland from climate science point of view, they are combined with the water cycle and the hydrological, and then the carbon cycle. And then we also think about this is an important part of the ecosystem and our survival, right? So it provides benefits of us and the wildlife. And then if you look at those the numbers, the wetland only cover about 6% of the total Earth surface, but provide the living environment for about 20% of the known species. So this is a very important, is people talk about the ecosystem services, about the wetland. So that's why at Nicholas School, they have so many, interests on the wetland studies. So in terms of the distribution of the wetland, so this is a paper published about 10 years ago to show what are those of the wetland. So here I would like to focus on more or less on the tropical and the subtropical wetland because it's mainly associated with the water cycles. And then the higher latitude, it seems for me, is more or less related with the temperature change, like global warming will release some of the help release the carbons. And then specifically for my project, I'm more or less focused on the southeast or eastern United States because this is kind of the, it's not the word. Yeah. So if you look at this, is a very dark green, shows that this is the wetland. So if you look at it, so the southeast is basically over here. So majority of the wetland, especially the subtropical wetland, is over the southeast United States, which is Duke. Duke is probably over here. So this is North Carolina. So we were here. So that's why kind of a pretty natural to work on this ecosystem. Another thing is like I mentioned, in the last couple decades, so clearly you see those the ghost forests, and this is I told Carol, Kyle in the morning we talk about when we go to the Congress to give the testimony about climate change, and then the scientists show one of the two pictures. One is the early age, the other is the latest, picture. So if you see the ghost forest, so when we talk about the ghost forest, we talk about those of the trees when they die without the leaves, they were still standing there. So from far away, you see this is the forest, but without leaves, we call that the ghost forest at the coastal region. So this is kind of the ghost forest. And then and also, if you look at the reference papers, about 50% of the wetland kind of degrading or disappeared in the 20th century. And when you look at those of the rate of the retreat at the wetland, so this is kind of like, sorry. So this is the yellow one shows the pre-industry level, and then the green one shows the post-industry levels. So clearly we see that the retreat rate actually accelerated, right? So this is pretty short. And then the bottom figure, so here is the Susan page over here. Like I mentioned, that just one event over the tropical regions. If you look at it, the carbon emission due to that fire over the peatland in Indonesia, so you see that so equivalent to 13 to 40% of the carbon emission. So this is a huge amount of number, right, in terms of a carbon cycle. And amazingly, climate model doesn't including that wetland ecosystem very well. One thing is that the wetland is so difficult to simulate it. The other thing is like there are very small scale features. And when you think about the grid box of the IPCC models, it's the current model is about 100 times 100 kilometers spatial resolution. So it's so hard to simulate it. And also we do not know the physical processes a lot in terms of this. So that's why I'm actually working on this. And today's lecture or seminar, I would like to share with you guys about, in the warmer climate, whether and when this wetland ecosystem will degrade. In other words, we're just talking about originally they're forest or they're grids, eventually they will convert it, or degraded, it becomes to ghost forest, or, the vegetation will gone, or I will show you some of the index later. And then once we do that, the second question we would like to know what are the processes or the mechanism really contribute to this degradation. So this is kind of like the two questions I would like to address or share with you guys. And like I mentioned, because majority of those subtropical wetland is over the southeast United States, like the Atlantic coast. So I'd like to focus on that, mainly because I live there and we have some of the in situ measurement for around a longer period of time. So this is the one with my, in terms of data, so we use some of the remote sensing data. So I will show you that the Landsat data we will actually use pretty much. And then we also combine with some of the OCO2 data in terms of the carbon. And then we will collaborate with the US Forest Services to talk about the forest inventory data, and then some of the observed the water table and mineralogical data. And at the coastal area, we'll also use some of the NOAA tide data. This is the only tide station within our region. So in terms of the coastal processes, we definitely need more of the in situ measurement to help us improve the model performance. And then we also take advantage of the physical-based model. So in this work, I actually have a really nice postdoc to develop the wetland models. We call that team wetland model. So this is the physical-based model, which tracks and predicts the change of the surface water, groundwater, salty water, and canopy waters. And then their size or the grade is a variable grade. So if the area, is relatively flat without a lot of the feature of topography, so, and then in this case, the grade could be larger. But if it is, they have a lot of topography, then the grade could be smaller. So they have, this is a variable grade, which can save a lot of computational time. And also we will simulate, in terms of all this processes in terms of the, the runoff, the infiltration, and then the evaporation, including the evaporation, transpiration, etc. So we'll talk about those later. And then the regional side, which is the Alligator River refugee areas. So this is a kind of a North Carolina, which is John King provide a long term of the data over there. So and then this is the area actually when you experience the hurricanes. So we'll talk about, besides those of the storm surge, the sea level rise caused the change, and also some of the fast events process will also contribute to the sea level rise, and then stronger wind or the heavy precipitation, etc. Right? So this is another. And then in terms of the overall features, so here I basically listed the Alligator River refuge area. So the elevation, kind of like below the sea level and to 7 meters above the sea level. On average, about 0.7 meters above the sea level. And then this top meter of the surfaces have a very high organic matters, and I actually get chances to visit the site, and we actually see how John's team, worked really hard to gain the data, and we saw the black bear far away, and then the snakes. So it's not easy to obtain those of the observational data. And then the climate condition is basically like the southeast, so kind of a pretty mild. So the temperature about 16 degree, 17 degrees Celsius, with about 7 degree in January and 27 degree in July. So we have a very strong seasonal cycles as well. And then the growing season about the area, about 195 days. So this is kind of give you some background about the location we're studying. And now how to identify the degradation of the coastal wetland. So we're not only focused on the coastal, but we also look at the freshwater. But here I will just give you some of the definition about degradation. So we will look at the NDVI value. This is the remote sensing index. And I believe all the people in the room will know what is NDVI, right? So yeah, so we will actually look at the NDVI values. So I will show you that shortly. So NDVI, if it is a very low, very small value, 0.1 or below, basically corresponding to the area of the rock or sand or snow. And then when it is its value between 0.2 to 3, this is kind of the medium values. So that is represents the shrub and the grassland, and with its very high values, and then like 0.6 to 0.8, then that is indicated is more or less related with the forest. So I'll show you some of the results shortly. So in our regions, so basically this is the area. So we will look at the open water or some of the vegetation, list the different vegetation listed here. And then I will show you some of the analysis. So this is our own analysis based on the long-term the Landsat data. So in terms of y-axis shows that NDVI. And then you see that we have 3 very different categories in terms of the NDVI values, and there are significant differences, right? Of course, we also have some of the very low values here. So basically, if you look at it here, their NDVI value are quite different significantly. So in this case, like we just talked about, in this category basically means that this is the forest, right? Like I mentioned. And then in between, we talk about this is kind of the, so we actually look at all the grade within the area. So we actually categorize in terms of the wetland types based on their NDVI values. So when the NDVI value is above 0.5, but less than or equal than 1, so that is represents the forest wetland, However, if it is between 0.4, 0.5, which is in this category. So this is called the transitional forest wetland. They are very different from the forest. And then that category over here, so which we show that this is an emergent herbaceous wetland. So their vegetation coverage is quite different, so that the NDVI value also separate. And then if it is that category over here, so this is talk about, this is a non-vegetated areas. So this is a 4 different type of the land surface, you can think about it, right? So this is what we actually based on the real observation to the categories. And then how we define those of the degradation. So in this case, we will think about the degradation as the loss of the wetland area. This is one way, like totally becomes gold forest, for example, that is one way. Or the loss of the wetland area or the impairment of the wetland function due to both natural and anthropogenic activities, and from which the system cannot completely recover. So this kind of a dynamic system, sometimes they can recover something, sometimes they cannot. So we will just look at those they cannot recover. And then including, so the second part that we'll talk about, the complete loss of the wetland. So this is kind of like the goals first, or the conversion of the structurally complex and multi-layer of the wetland types, like the forest wetland, to the less complex and functional wetland. So for example, we were changed from the forest wetland to emergent herbaceous wetland. So this is kind of the degradation by definition. Okay, so based on that, we can define this 6 type of the degradations of the wetland. The first type, we will think about the forest wetland. So forest wetland could degrade to non-vegetated area. So this is forest, becomes ghost forest. So this is one type, right? And then the forest wetland could degrade to emergent herbaceous wetland. So they still have some vegetation, but not that, multi-layer or not structured. So this is another type, wetland. So in this case, we're talking about originally the forest, their NDVI value were within 0.5 to 1. And then for this type of the degradation, so their NDVI value have to be, changed less than 0.1 based on the category were defined on the prior slides. Right? So this is the one. And then the forest wetland could also degrade from the forest to the transitional forest. So their NDVI values at the very beginning will decreases, but not that dramatic like this 2 type of the degradation, right? So all from 1, 2, okay. So this is the first for the forest wetland. And then we'll have another transitional forest wetland. So they can only degrade it to either the non-vegetated area, or they can degrade it to the emergent herbaceous wetland. So we're just talking about they becomes bad and even worse, right? Instead of the recovery, right? Remember. So this is a transitional forest wetland. At the very beginning, their NDVI value were within 0.5 to 0.5, right? 0.4 to 0.5. If it is totally changed to non-vegetated, so the NDVI value should less than 0.1, right? This is another type. And then if the transitional forest wetland, they degrade it to emergent herbaceous. So original NDVI value within 0.4, 0.5, they will change to 0.1 to 0.4. So this is what we talk about, another type of degradation, right? And then for the emergent herbaceous, they can only change to non-vegetated. Any questions so far? Okay, very good. So this part is a little bit more of the, and then let me use one of the grade to show you an example. So this is one of the grade. So at the very beginning, we have the data. So you see that their value is about very close, 0.5, right? So you can think about this is about, the forest wetland at the very beginning. And then you see that we do have this kind of the seasonal variation, internal variation, but overall they have a trend, right? A trend. So when we started, we actually look at, a couple of, years to make sure their original is the forest wetland. Okay. And then later on, once when we publish the work, so you see that their NDVI values were actually below this kind of 0.4. So we would think about, they were not a comeback during the period of time. So we're thinking about that specific grade is actually experienced a degradation from original forest wetland to this emergent herbaceous wetland because the NDVI value is less than 0.4. So we actually check all this grade box within the analysis domain, right? Analyze them. So we actually look at it. So in this case, originally their forest wetland, by the end of the analysis period of time, they converted into the emergent herbaceous wetland based on the NDVI values, right?
Excuse me.
Uh,
Deforestation, do you have deforestation on the wetlands?
mm.
So my question was actually, what is the stronger effect? Does it come from deforestation and climate or both of them at the same time?
Yeah, you are talking about the anthropogenic deforestation. Are you talking about?
Yes, yes.
Okay, yeah. So because this is the site, you know, the area which is preserved, which is not that many of the anthropogenic deforestation. Yes, but in reality, if you exploded, you know, extended your area to a larger, then that aspect you need to consider. Yes, yeah, yeah. So we're talking about how climate change in terms of drought events, flooding events, or associated with increase of the greenhouse gases and sea level rise, all these processes will influence the wetland ecosystem. And then we do not count for those of the ecosystem, including the humans deforestation to cause the wetland total change. Yeah.
But is the degradation of the wetlands cause the deforestation?
I think like,
That is not.
this is a kind of a, you know, the processes are like the drought events or the heavy precipitation is the climate phenomena, extreme events, but due to the global warming or due to the climate change. So in that case, it's still related with the climate change, but not directly like people will just cut the tree. So this is a kind of like a climate field to discuss about, you know, how climate change will influence. When we see the climate change impact, we're more or less talk about how warming climate first influence precipitation temperature, therefore influence the ecosystem. And then deforestation's impact, which is different from that. Yeah, but very good for clarification. Any other? If not, so we will look at how the whole different processes. So this is kind of a lot of work which is carried out by my students. So we will first look at those of the NDVI, you know, the data from the Landsat, and then you have to you know, deal with the cloud contamination and then validation. And then we will actually look at all the gray box and then to identify you know, the forest or the forest wetland or different type of the wetland, and then we categorize each time of the gray box in terms of their wetland type. Okay, and then we will actually analyze each grade based on the starting point to the end and see whether, like the previous slide shows, that whether they have a systematic change or not. So let's look at what are the result done by my students and the postdoc. So this is the wetland degradation result. So first of all, on your left, so this is which we talk about the first type of the degradation. In other words, we talk about the forest wetland degraded to non-vegetated areas. So we found that within the analyzed domain, there are about 930 grades will change from original is the forest into totally non-vegetated areas. They could be ghost forests, it could be totally swamped by water, ocean water. So this is actually, I'm not sure whether you can see that clearly. So those are the areas which actually experience those of the degradation, mainly on the coastal regions, So this is a total of 930. And then the middle one shows that the second type of the degradation, which means we from at the very beginning is the forest wetland, and then they change to the merger the herbaceous wetland. So you see that comparing to the first type, we have more of the grades experience this type of the degradation. And then those of the left shows that those are the areas which experiencing those of the degradation. And then the third type was still at the very beginning, they are forest wetland, then eventually they were degraded to the transitional forest. So this is the largest part of the degradation among all the three associated with the forest wetland at the very beginning. of the analysis period. And then this slide shows that the last three degradation now, so two of them are associated with the transitional forest. So this is the transitional forest wetland at the very beginning, later degraded to non-vegetated area. So transitional, I draw a kind of a cartoon to explain that this is the transitional forest wetland. Later on, they were totally gone. So this is the type. So we are about 1,276 grade. And then the middle one shows that at the very beginning, they are transitional forest wetland, then degraded to the herbaceous wetland, so kind of a grass type of the wetland. And then the last one is just for those of the emergent herbaceous wetland at the very beginning. So they are original, they are grass, and eventually they are totally gone. So mainly associated, you can think about have some of the grasses at the coastal region, and then the sea level rise, they are totally gone. So kind of related with that type. So this is what we look at in terms of the degradation at different locations, right? And then the student actually plotted all these 6 types of the degradation, use different colors so that you have a feeling about the 6 type of the degradation happens at where. So this is illustrated on this plot. And then we will actually see that the degradation are more or less over the coastal areas, some are stronger, some are, some type of degradation less, but generally speaking, all these 6 types more or less focus on the coastal regions. And then this table actually illustrates when that degradation happens. Remember, like I'll show you, it's not at the end of the analyzed period, the degradation happens. So basically we'll show that each year, this is the 6 type of degradation. And then we will show that, the number of the pixels of the wetland degradation happens in each year. So for example, we'll see that 2014, the first type of the degradation, we found that within our areas, we have 182 of the pixels experience that type of the degradation. Okay. And then the second type, you can also see each year how many of the pixels will degraded. So once we found the degradation happens in that fiscal year, they will never come back. Okay, so we're just look at they are going that direction instead of the reverse. So all this shows that at which year we will look at it. So in the future, for example, like the NC government, they actually ask us to collaborate with the local organizations to give us a plan which area maybe experience such kind of the degradation, whether they need to take actions to mitigate such of the degradation, right? So this is a kind of like the survey also help them to understand that. And that's why our model could also help project once we give the future predictions as the forcings. So this is a kind of the areas or the numbers where those of the degradation happens, Basically, we found that these 2 years, for some reason, seems have more of the grade or more of the grade box experience such kind of a degradation. This is a kind of the thing. And then this is the first part we will talk about. And then the second part, we would like to understanding what are the processes or the mechanism really contribute to the degradation, So here, I would like you to think about Yingtan published a paper is really helpful to understand. Like I mentioned, the subtropical, tropical wetland are more or less related with the groundwater level changes instead of like the higher latitude, the wetland or the peatland are more or less temperature dependent. So here we will talk about different locations in terms of their systems. So coastal wetland, more or less, we can think about the sea level rise is definitely play a bigger role as well, right? When we look at the freshwater wetland, then the groundwater table is also very important. So their migrations is more important. And then A is really the precipitation local runoff fleet, the wetland. So once we go to the coastal areas and then the surface water that, and it's more important that groundwater will also support that water level changes. And then, so in this part, we will actually give a systematic diagram to look at what are the processes. So we will actually simulate how does groundwater, the fresh water level changes. So in this case, you can think about this is different wetland ecosystem from the freshwater to the coastal, waters. And then our model, I talked to Holly this morning, we were only we do consider the sea level rise, but we do not consider the model need to be improved in terms of the gradient of the salinity. So we were only look at the boundary between the freshwater and the salty water at the moment. So so this is kind of like talk about, once you think about this is the surface water, and then this is really talk about the fresh water, and then here we talk about the salty waters. So when the salty water intrusion comes in the past, those are the freshwater wetland, maybe those are the vegetation will tends to die, right? Because the salinity level increases. And so this is kind of thing. And another is like, if think about if there have a drought events and then the groundwater will be lower because of the higher evaporation. And then that could also cause the freshwater wetland, their vegetation in a not healthy environment. So this is combined with other like the stronger hurricanes or whatever, a stronger wind, for example, then maybe could also cause some of the degradation as well, right? So this is a kind of the things. So we would like to see what are the disturbances induced by climate change or climate variability as well as the sea level rise. So this mainly including the drought. So let's think about the drought happens, groundwater level also changes associated with that, right? And then we will also talk about the hurricanes. So hurricane is a little bit complex, so they can directly ruin the wetland through very stronger wind, so that the tree will totally, fall down. And then, but maybe they can, after a couple of years, they will recover from instead of the tree, they maybe have some syrup, and then they can also bring a lot of salty water into land as well, right? And then inundation, so associated with the stronger flooding events, and therefore to cause some of the degradation, right? And then the sea level rise, for example, this is also another very important factor we need to consider. So all these processes will actually consider for the model simulation. And then we would like to see, so this is a paper published by my former postdoc. So we'll talk about how those of the changes, climate variability, climate change. So in terms of change of the frequency and intensity of the precip. So this is including the drought events and the flooding events happens over here due to climate change. And then change of the temperature also includes the evaporation, right? And then the sea level rise, and then how all these parameter changes will first influence the water storage, or the water movements. So all this, number one is the hydrological perspective, and therefore they are also influences the biological productivity, and then the carbon storage, and then the geomorphologic change or the nutrient flow. So we're more or less focused on this level. So this is the key here to understand the wetland ecosystem. So this is why we will study the hydrological. And then, like I mentioned, the wetland have this degradation, but some type of degradation could be reversed, So a lot of time we talk about the tipping point. So we will look at the tipping points instead of they can recover. And Emily Bernhard actually also used the same methodology to look at some of the recover as well. So this, and our paper more or less focus on those of the change, but cannot recover at all. So we're using environmental data, we quantify the wetland, the hydrological resilience to the climate variability or the climate change, like I just mentioned, at the regional scales. So we were using this model, a very sophisticated model. So this is the PIM model. So this is the Penn State integrated hydrological model. And then we actually add a wetland module to help the understanding what happens within the wetland ecosystem. Like I mentioned, this is the regional skills instead of just a very, watershed skill, very small skill. So I personally like to see how the regional skill or eventually the continental global skill, how the wetland will change and therefore influence the water cycle and the carbon cycle. So that's why we will look at the large scale. And then this is kind of like the physical based, including all the processes, but definitely the coastal process need to be improved. Like I mentioned, we only consider the boundary between the freshwater and salty water. We do not consider the salinity level gradient, and therefore cause the change. And also like my colleague at the same department, we call that division. So who is coastal person which talk about, the geomorphology changes. So we talk about deposition, and then that actually add another level of the complexity of the problem. So right now we do not consider like the coastal will shift associated with that. So we're kind of fix the coastal line, and then the salinity is kind of the boundary between the salty and the freshwater. But we can simulate pretty well based on, like everybody really wish to know the equations, right? But just tell you, for those of the people who are interested, like Professor Hu's group, maybe later you can read those. And then we will also including the coastal process like the tide and sea level rise, and then we will kind of simulate the salty water intrusion based on this kind of the formulas. So for those of students and faculty who are interested in this part, we can discuss about later. This is more or less kind of a computational processes. So right now I'd like to show you some of the model simulation against observation. First of all, we wish to know like the model could do the job, right? So here is the simulated versus the observed. The observed is on the x-axis, and then the vertical is the simulated. And then you basically see that a different variable like a simulated evapotranspiration, and here is the simulated groundwater table height. And then this is kind of the simulated soil water content. And then this is the water level change at different seasons. You use different colors. But generally speaking, you see that the model simulated quite well or reasonably well in terms of comparing to the observation, from the observation. And then we also compare, besides in situ measurement, we also compare the model's simulation against the evapotranspiration product from NASA Modi's product. So this is kind of like the simulation, and then with the model simulation, and then also compare with the observation is actually the blue dot or blue line show here. And then this is the kind of the spatial patterns in terms of the models, and then to our simulated. Because models have a relatively coarse resolution, so comparing to ours, it's a little bit different. But generally speaking, the model conclusion at the bottom, we see that it's kind of do a reasonable good job in terms of simulation, those of the hydrological processes. And then we would like to see the regional scale groundwater behavior, and we will also look at the topography, how they control the groundwater at the upland, more or less related with the freshwater wetland. And then we will also look at how the recharge control the groundwater at the lower flow plains at the coastal areas. So we also compare those as well. So give us a kind of a confidence to use the models. So right now, I would like to show you some of the results. So this is a kind of like the inundation, in other words, the flooding events, how the flooding events will cause those of the wetland degradation. And so we actually use the model to simulate it from 2007 to 2016, about 10 years of the hydrological processes will focus on the inundation. We found that within our areas, nearly half the study areas were actually experiencing the inundation sometime during the simulation period. And then the coastal wetland regions, their frequency in terms of the inundations ranges from 5% to barely happens, or to 100% always happens each year. So 2/3 of this occurrence actually have a frequency higher than 50%. So you think about the areas actually have a lot of inundations, at least half of the regions experience those. And then this is kind of like the hydrology, how that will influence by those of the climate change and the climate variability. So here I will basically show that this is the precipitation. Not sure like the left is the precipitation from 1995 to 2014, and then this is temperature simulation, and that is sea levels. So you also see some of the observation, the different colors really show us about, the different seasons, and then this represents the 1 standard deviation horizontal line, 2 standard deviation horizontal line. And then that is temperature. Temperature doesn't change much from year to year, but precip does change pretty much. And then sea level, you can also see sea level rise for sure, right? And we actually could, based on those of the precipitation, could define some of the dry year and the wet years based on those of the precipitation in terms of their exceeded the standard deviation. So we find that among the 20 years of simulation, we have 3 years of the wet year and 3 years of the dry years. And then we do some of the analysis corresponding to those of the flooding events. The wet year corresponding to flooding events, dry year to drought events, right? And then some of the sea level rise. So right now we would like to see the forest wetland, how they respond to this groundwater level changes. So this is a kind of the simulation indicating the seasonal annual mean groundwater at the coastal forest wetland from 1996 to 2014. So the groundwater during the dry and wet year will flow into different colors. Dry year we use the orange color, the wet year we use the blue colors. And then the horizontal blue line shows this is the climatological meaning of the winter groundwater level. So basically I see, I guess you probably agree with me that the annual levels, the groundwater varies between 0.02 to 13 centimeters below the ground, below the surface, right? So this is kind of the variation range. And then the internal variation in terms of the groundwater highly correlated with the precipitation. So we actually calculate the correlation coefficient about 0.95. So in other words, precipitation definitely largely controlled that groundwater table. And on the seasonal scales, we see that the higher groundwater in winter time and lower is in the summertime. It's a very easy to understand. In the summer, temperature higher and the evaporation will also higher, right? So this is a very, and then the groundwater table tends to return to its long-term climatology every winter, except those are the extremely dry years, which I just listed over there. So this is kind of like the forest wetland in terms of the groundwater changes. So what are those of the 3 years? I actually like to see those of the years you see over here. So they are not coming back to the climatology. So for coastal forest wetland, if you think about they tend to be resilient, in other words, internal variations, or look at how drought influences. So if the annual precipitation is not 2 standard deviation lower than the climatological mean precipitation, they cannot come back to the climatological mean position. And then for those of the herbaceous wetland, so we use the same plot to show you, and then you see that the groundwater table varies, kind of similar, but more or less shallower. So 0.02, 5 meters to 0.1 meter below the surface. And then they are also highly correlated with the precipitation as well, the coefficient 0.91. And groundwater slightly increases with time. It's probably due to the sea level rise, probably due to the sea level rise, due to the period of time, and then we also look at how this hydrological resilience to the climate dryness. So in this case, we will look at, instead of the seasonal and the intentional scale, we actually look at the daily scales. And then we actually show that this is the forest wetland on the top. And then you see that, so those are the wet years plotted in blue, and then this dry years plotted in yellow. So for dry years, it's kind of the water table kind of remain at the same level during the dry years, right? But then the water level slightly above the, it kind of about 10 meters higher than those of the dry years. And when you look at comparing the wet and dry years, water level height. But then for the dry years, we do see some of the rock climate change. Usually I think like when the precipitation, the dryness were longer than 6 days, you see that the groundwater tends to be decreases to pretty dramatically. So we would think about probably 6 days in terms of the dryness, maybe the threshold for those of the forest wetland at the area. And then if their drought, like the flash flood, drought, 2 or 3 days, maybe not that harsh to the wetland, forest wetland ecosystem. But then the bottom shows that the herbaceous wetland. So I think like for those of the dry and wet year, we didn't see huge differences comparing to the forest wetland. So when you think about, the dry year will not really influence those of the herbaceous wetland ecosystem, comparing to the forest wetland. So we actually get the conclusion for this part. We talk about coastal forest wetland is more or less resilience to the dryness, especially duration of the dryness is shorter than 6 days. However, the herbaceous wetland is not really suffered due to the dryness or the drought. And then we will also look at how the flooding events will cause some of the degradation. So in this case, we draw that the overland flow. So you think about this is the wetland, and then when the flooding events happen, they were totally swamped. So we call that overland flow. So this is the dry years, and then that is the wet years, and then different color represents different season. So this is also based on the daily scale simulations. So we do find that when precipitation were more than this 43 millimeter per day, this is a pretty high rainfall rate. So the large overland flow rarely occur when the precipitation will not reach that level. It seems like for me, this is kind of like so this is probably because the lower soil moisture content in the dry year providing sufficient water to storage of those of the heavy precipitation. And then for those of the dry year converted to the, for those of the wet years, so if you have a precipitation, even it's not that high, like 33 millimeter per day, but then the overland flow seems much higher than those of the dry years if you compare the magnitude, right? And then the higher flow rate occurs in almost all seasons. So this is a kind of like how those the flooding events will influence the wetland ecosystem in terms of the overland flow. For wet years, that is even bad, even worse for those in the wetland ecosystem. So the wetland ecosystem is less resilient to heavy precipitation during the wet years, even though they're not extreme. And then we will look at the spatial variation of the overland flow during very large of the heavy precipitation events, including those of the hurricanes. So here we show the y-axis shows the overland flow from the cubic meter per day, and then how that change associated with the elevation change. And then the right figure shows the spatial distribution of the grid box with a very high and extremely high overland flows. So very high is a green color, and the extremely high is kind of the the orange color. So we will tend to identify the overland flow rate because of the high overland flow can cause erosion, therefore harmful to the wetland ecosystem. So we find that the areas where sediment erosion could occur occupies majority of the place of the domain. In other words, when we talk about the very high overland flow and extremely high of the overland flow, so 39% will actually observe those of the erosion, those of the higher erosion. And then once the high erosion happens, and the wetland tends to degraded. And then we also look at some of the subsurface flow as well. So that is surface, this is subsurface. So basically give you the kind of the same result, although the domain will actually change slightly, only a quarter of the domain will experience subsurface flows, so is with the rainfall events. And then we'll look at the sea level rise. So this diagram to show that the seasonal and intended variation of the sea level, salty water table. So you can think about this is the kind of the salty water intrusion. Now, remember we just talked about the boundaries, the fresh and the salty water. And you see those of the dry and wet year will also plot into different color as well. So the intended variation were much smaller, mainly because of the pretty slow of the salty water diffusion processes. On the seasonal scales, the salty water table varies kind of within 3 centimeters based on our simulation. And then 2007, this is a kind of a year, the annual salty water table increases with the increase of the sea level, and the salty water intrusion is more sensitive to long-term sea level rise, So this is kind of after 2007 seems like increase the salty water depths. And then this is also, I think like this is the sea level changes. So if you compare those two, it seems give us the result over there. And then the difference of the salty water table and extremely dry and wet periods. So this shows the difference between those two, different scenario, very dry year or very wet year, the differences between that. So we see that the salty water table actually between extremely dry and wet years, it's kind of like showing here those of the spot area. Show that the very high differences is kind of 100 meters from the coastline, and this is those are the areas. Then the state government need to know like which is very sensitive to the sea level rise. So if they need to take action, they should work on those hotspot locations. So this is which basically what we're talking about. And then the animation basically shows that how this degradation happens with year. And then we will see those of the threshold of the wetland degradation from the forest wetland, the transitional forest wetland or emergent herbaceous wetland, how they degraded. So this animation basically shows that where that happens and when that happens throughout the year is at the top. So that the policymakers need to take action at the North Carolina coast regions. And then the left basically will talk about where those of the degradation happens at the coastal regions, So this is a kind of the picture we will actually present it at the NC state of the government, like the governor. Group. So I would like to summarize a little bit about today's talk. So we would think about the peak wetland could do reasonably good work in terms of simulate the regional scale of the wetland degradation. So we think about the regional scale simulation actually shows that the transition between the region with topography, control the water table and the region of the recharge control the water table. So today we're just more or less focus on those of the coastal one, but freshwater wetland also have those of the more or less focus on those of the drought events or flooding events impact as well. And then we also find that within the studied area, majority of that, 82% of the area is likely to have those of the sediment erosion, therefore cause the wetland degradation. So this is based on our analysis. And then we think about the groundwater table, overland flow, and salty water intrusion. Those are the factors to influence the coastal wetland in terms of their resiliency. So we're talking about the freshwater, the salty water wetland ecosystem. And then the threshold, we can identify some of the threshold, like I show you the 6 days of the dryness is definitely a threshold. And then, but under the hydrological process state and then sediment transport could be changed when climate condition will also change as well. So this is a kind of dynamical process. So currently, my formal postdoc at Los Alamos National Lab will continue work on that. So we're hoping to incorporate the future projection from the IPCC models output into this hydrological model to project in the future down the road where those of the degradation continue to happen at the Southeast United States. And then what are the tools or mitigation ways we have to take actions to prevent the loss of the wetland ecosystems. Yeah, I think I will stop here and thanks for your attention. I know it's a lot of text. Hopefully it's not boring everybody for the modeling simulation. Yeah.
Yeah, so you talked so my background is climate variability, so I'm interested in that aspect, especially because you talked about interannual variability being a large component to understanding like the groundwater table variability, especially. And there's that difference between the dry and wet years. So I'm curious, knowing that the Southeast US has a strong ENSO signal. Do you know, do you have any idea of ENSOs related to understanding the wetland degradation? Is it predictable possibly on the seasonal time scale? Like if certain years could have a higher likelihood of degradation or not?
Very good question. So I think like ENSO definitely play a big role in terms of modeling the weather and climate in the Southeast, right? But not always. So I actually talk about this with the state climatologist. So we think about the past winter is the La Nina year, right? So our region is supposed to be a little bit drier, but not the case. Why? Because maybe that's just a personal experience. So at North Carolina, on average, we experience 1 snow each year. Last year, we do not have any snow. This year, we have 2 snows. So it's not only influenced, in other words, I think the precipitation or temperature is not only influenced by ENSO, but also the high latitude systems like the polar vortex, whatever, So this is pretty hard to make the prediction. If we know that this is a year in terms of how much precipitation really happens, then that's really helpful for us to do the prediction. Yeah.
Oh, I had so North Carolina is, removing dams. And I suspect that both of the rivers that are on either side of this wetland are dammed, given how, how many times North Carolina's river, there's like 30 dams on our river. And so I was wondering if you have looked and seen, is there, were dams constructed during your study period, or were they removed during your study period? And is that potentially also related
Yeah,
to?
so that's a good question. In other words, when we think about how the human activities directly influence the wetland, resiliency, right? So at the current stage, we didn't look at that. And also people think about instead of deforestation and dam, they also think about people were set up those the drainage system as well. So that is more or less on the very local or very small scale features. So we would have like to think about to collaborate with the local peoples, to understand how that specific activities eventually will cause this wetland degradation changes. For example, people mentioned that if we use the drainage system, then we can bring more of the salty water, maybe harmful for those the wetland. But then the drainage system does, they do have their own benefit as well. So it's kind of like we need to quantify the pros and then find a balance within this. But it's definitely a very good question for the policymakers. They have to make the decision.
Yeah, hi, it's very nice talk. So, you showed a figure, showing the NDVI.
At the very beginning.
Yeah, change. So, I just want to ask, how should I interpret that figure? Should I take it as a trend? Or because you also mentioned the tipping points later on. So, or it's like a stepwise change after a certain year, then we see the big drop.
Yeah, let's see, so right now, so probably this figure, right?
Yeah.
So, like I mentioned, so for our studies, we were just focused on, it could be stepped. So for example, one is like the good one, and then they were totally gone. Like, in the past, there are forests, and then big events will cause them totally change to the ghost forest. So that is step function. It could be like what happens gradually have a trend to cause the degradation. So it really depends, So some studies actually show that, for example, the hurricane events. So hurricane, once it comes, the very strong wind and the huge amount of precipitation, and then bring more of the salty water into the land, maybe can cause some suddenly change of the degradation. But after a couple of years, it could be recovered, right? So in that case, we will think about, then we will not including into this degradation. We will think about, no matter this is a trend or suddenly happens like the step function, in any case, they will not come back. Yeah. But there are some of the different type of the species, they may come back to this, like getting better, more or less within the transitional or forest wetland. So like Emily Wenhong, they have a publication to look at that aspect as well. But for us, we would like to see they were change, maybe gradually, maybe suddenly, but they cannot come back. Yeah. So we would like to see it's not really reversible. In reality, for example, like within how many grade points of grade box. So maybe they have more of the grade box at each year's will change. But what we draw here is that the change will not come back.
Well, maybe you'll know this. As we know, the area seasonal variation.
That's right.
So it's about the annual rate.
we will actually use the maximum NVIDIA. So that we will actually make sure it's compare apple to apple instead of like considering seasonal variations. Yes. Yeah, very good question.
I was wondering, I don't know if I missed it, about to what extent the model has been validated, or what kind of data that you actually need to validate the model.
Okay. Have a very good and broad question. So I think like I did show some of the model evaluation. Remember I showed that one axis is observational, y-axis in terms of the ET or groundwater or soil water content, etc. So in terms of those, the model seems did very well, but in terms of the ocean processes, like because we only have one tide observation at the whole area. So that part I'm not 100% confidence in terms of the ocean processes, in terms of the sea level rise, because we have only one station. But this is the current status we have, so we were hoping we can set up more of the tide in the station so that we can have more data to look at different location at the Atlantic coast so that we can, tune the model parameters to make it more accurate on the regional scale.
So the three most important processes or the parameters, one is the groundwater table, one is the overland flow and saltwater intrusion. Those are the key parameters.
Yes. But then a lot of processes related with those, you
Right,
have those.
I was wondering the same thing because we work in very small scale things, well. So I don't know how to reconcile, or if we talk about the larger picture, talk about the degradation in general. Just wondering, do we need to know all the details of what happens during the process?
That's always a good question. We talk about this, some, like my collaborator, they are just on one side, right? So they look at very detailed, processes and then the parameters. But we look at the regional scale, some of the processes maybe not that important, right? And also the model cannot simulate very, very fine. So currently I actually use the 30 meters, resolution, which is very expensive simulation. So I have to use the Duke supercomputer and then the OnCars parallel computing system to help us to run the models. And so this is the process. So we do have to look at what are the most important processes and then to neglect some of the details to make sure we can capture the first orders of the features on our screen. But it's that.
So thank you all for your question. In the time, we have one last question to ask. If not, please actually join me in thanking Dr. Lee for your wonderful talk. Thank you.
Well, where you were